Okay, in this video now, we'll look at change of base formulas. So here, what we see is that we have a to the power x. And let's say a to the power x, I want to change it to b to the power something. So how do I change a to the power x, whose value is same as a to the power x, to be b to the power something? Okay, so the claim is that a to the power x is same as b to the power x log ba. Okay, how do we prove that? And of course, if b happens to be e, right? So it becomes log b becomes natural log a. So it becomes e to the x natural log a. All right. So now how do we prove this? To prove this, if I want to change a to the x to b to the x, so I can do b to the log to the base b, right? Because these two cancel, so I can add this anywhere. So a to the x is same as b to the power log b of a to the x. Okay, and then obviously log of a to the x is x log a. Remember the property? So this becomes b to the x log ba, and that's what this is. Okay, so pretty straightforward. And now if you want to change log of a to log of b, so if you have log of to the base a of x, it is same as log of b to the base x over log of b to a. How do we prove it? Okay, so what we need to prove is that log of ba times log of ax is equal to log of bx. This is what we have to prove. Now, in order to prove it, what we will do is we will say, let's do b to the power this thing on both sides. So the right hand side, obviously this and this cancels, we get x. Okay, what about here? What happens here? Okay, so here we are saying b to the log ba. So this is same as saying this here to the power this part. Remember, b to the power a to the power c is bac. So the product becomes this to the power this to the power this. This just becomes a log ax equals x, and of course x equals x. Therefore left hand side is same as right hand side. So that's the proof for this statement. Okay, now we will do the last topic in this chapter. Okay, these are the proofs. So here they're saying calculate log 37 with the change of basis presented earlier. So log of 3 to the 7 is same as natural log of 7 over natural log of 3. In fact, log of 7 on any base or log of 3 in any base. So we can choose it to be e, so it becomes this, and you can calculate it. Okay. Now the last topic is hyperbolic functions. What are hyperbolic functions? All right, so you see that these hyperbolic functions are defined in terms of e to the x. The question is, where is the motivation for this? One thing is, which you might have seen before, that you can prove that EIX is equal to, it's a very, very famous Euler formula, cosine x plus I sine x. EIX is cosine x plus I sine x. So remember this. It's an extremely important Euler formula. All right. So therefore, if I do e to the I negative x, that would be cos to the negative x, which is same as cos x, plus I sine negative x. But sine of negative x is negative sine x, so this becomes negative I sine x. If we add these two statements and then divide by 2, because if we add 2 cosines, it becomes 2 cosine x. If we divide by 2, it becomes cosine x. So if we add these two equations and divide by 2, this and this will cancel, and we will get cosine x is EIX plus E negative IX over 2. Similarly, we can prove that sine x is EIX minus e to the negative ix over 2i, right? So anyway, so this is what we get for sine, cosine, tangent, and the normal trigonometric functions. Now, if we replace EIX by EX, of course we get different functions. So here, pay attention that if you look at cosine x, which is EIX plus E negative IX over 2, if we replace IX by x, we get a new function and we call it cos hyperbolic x, cos x. And that is defined as EX plus E negative x over 2 as compared to EIX plus E to the negative IEX over 2, which would actually give us cos x. So this is cos x. Sine hyperbolic x is EX negative minus E to the negative x over 2. In reality, sine x is E to the IX minus E to the negative IX over 2i. And then tan hyperbolic x is the ratio of these two. Okay? And then hyperbolic cosecant is 1 over hyperbolic sine, hyperbolic secant is this, hyperbolic cotangent is 1 over tan hyperbolic x. So that is very similar to our regular trigonometric relationships. Okay, so these hyperbolic functions are important in later on when you learn more mathematics in differential equations. So they're useful in many applications. So here in calculus, we'll be introduced to them. So what we find out is that if you do cos hyperbolic square t minus sine hyperbolic square t and use the definitions of these two functions, plug them in, what you find out is that cos hyperbolic square t minus sine hyperbolic square t is equal to 1. As compared to if these were trigonometric functions, it would have cosine squared theta or t plus sine squared t equal to 1 plus. Now it's replaced by minus. And what it reminds you of is that if you call this x and y, x squared minus y squared equals 1. And that is a hyper equation of a hyperbola. And that's why these functions are called hyperbolic functions. To draw the plots of these, so cos x was e to the x plus e to the negative x over 2. So if you plot ex, half ex, which is this function, then half e to the negative x is this function. When you add these two, you get this curve. And therefore this curve is the cos x. On the other hand, if you do half ex, right, this function, minus the red one, or you say let's add it to the negative of this function. If you make it negative, it flips down, it's this one. Add these two functions and you get hyperbolic sine. And then if you take reciprocals of these functions, like 1 over cos x, so this is 1, stays at 1, and as it goes up to infinity, it's going to 0. 1 over infinity is going to 0, does this, and same is symmetric on the right hand side. So it's an even function. And this sine h is an odd function. When we do 1 over this, at this point when it's 0, it becomes infinity. On the right, 1 over this stuff is positive, and negative stuff, 1 over negative is this. So this becomes cosecant x function. And then finally, by taking the ratio of the top two functions, sine h and cosine h, we get hyperbolic tan, and we get co-hyperbolic tangent functions. And now, based on the definitions of all these functions in terms of ex, right? So cos x, for example, was e to the x plus e to the negative x over 2. And hyperbolic sine was e to the x minus e to the negative x over 2. And so on. So if you use those definitions, we can easily prove that these relationships hold. So these relationships are extremely similar to what we had for trigonometric functions. Remember, cosine negative theta was cos theta, sine negative theta was negative sine theta. So same kind of relationships, similar relationships are true for hyperbolic functions. And these, of course, come directly from the definitions of hyperbolic or cos x and hyperbolic sine x. Now, remember, sine squared theta plus cos squared theta equals 1, which came from Pythagoras' theorem. That is replaced by this relationship here. And then if you divide both sides by cos square x, we get this relationship. Or in equation 5, if you divide by hyperbolic sine squared x on both sides, we get this relationship. And number 8 and number 9 are exactly the same as the relationship of sine a plus b is sine a cos b plus cos a sine b. So there, replace these sines and cosines by hyperbolic ones and you get the same relationships. And all of these can be proved by using the definitions of these hyperbolic relationships. Okay, now an example. So we are told to simplify hyperbolic sine of 5 natural log x. So we use the definition of hyperbolic sine, which is hyperbolic x is e to the x minus e to the negative x over 2. But replace x by 5 natural log x. So it becomes e to the 5 natural log x minus e to the negative 5 natural log x over 2. Now this 5 goes up, this 5 goes up, we get here. And then these cancel and we get this relationship. Okay, then if hyperbolic sine is given, we know this relationship and we can plug this in here and we can obtain the hyperbolic cos or cosh. And once we have hyperbolic sine and cosh, we can get hyperbolic tan, this divided by this, and then we can also get the rest of these three. These are reciprocals of cosh, hyperbolic sine, and hyperbolic tan. Okay, and finally, we can obtain the inverse functions for all these 6 hyperbolic functions. And we can prove that they are these expressions, natural log expressions. Okay. So as an example, if you're given, find inverse of sine hyperbolic 2, just plug in the natural log function and obtain the result. And same thing over here. And that finishes this chapter.